Hi everyone. So I thought I would make this video on important pages of the ESRT for our unit Meteorology 1. So the first place I want to start is on the cover page with our properties of water. Now we have our three states of water, our solid ice, liquid water, and gas phase, which is our water vapor. So on this chart, we start off with the melting process, which is going from solid to liquid. And in this process, this chart shows us that we are gaining energy and we are gaining 334 joules per gram of for every gram of ice to melt it into liquid water. On the reverse, when we're freezing liquid water into solid water, we are releasing energy and we're releasing the same amount, 334 joules per gram. So for every gram of liquid water you have that you want to turn into ice, you need to, in theory, take away 334 joules for every single gram of liquid water that is turning into ice. Our third property here is vaporization, also known as evaporation. That's when our liquid water goes into our gaseous phase, our water vapor. We are gaining energy here, just like if you were to boil water, you need to turn on your stove to give it energy in order to evaporate. This phase change takes 2,260 joules for every gram of liquid water to turn it into water vapor. Our fourth process here is condensation, our very important concept for this unit. So condensation is when water vapor is turning into a liquid. And for this process to happen, we are releasing energy and we are releasing 2,260 joules for every gram. We're releasing this energy to cool our air temperature to our dew point. So that cooling process is our releasing of energy. And once we cool to our dew point, water vapor turns into liquid water. So an example here is how much energy does it take to melt 10 grams of ice? So what I would do is I would take my 10 grams, that's my ice, and I would multiply it by 334 joules per gram. The grams cancel out, leaving our units just joules, and the math works out to 3,340 joules in order to melt 10 grams of ice into liquid water. So that's on page 1, our cover page of the ESRT. The second page I want to talk about is page 12, and specifically our dew point chart. On the left-hand side, we have our dry bulb, which is our air temperature. So from top to bottom here, we go from -20 all the way down to 30 air temperature. It's always in Celsius. On the very top, we have our difference between wet bulb and dry bulb temperatures. So to obtain this information, our dry bulb minus our wet bulb equals our difference. So in our wet bulb is measuring the amount of water vapor in the air. So an example here to use this chart, say we had a 20 degrees Celsius dry bulb and a 10 degrees Celsius wet bulb. We would calculate our difference to be 10 degrees Celsius. You would find your 20-degree dry bulb column on the left-hand side. So our answer for our dew point is somewhere across this line. To find out exactly where, we take our difference, our 10 column, and then where they meet up is our dew point at -2 degrees Celsius. So when our air temperature, 20 degrees Celsius in the example, cools to this number, -2 degrees Celsius, that's when condensation will occur. Water vapor in the air will turn into liquid. Now, on that same page, we have our relative humidity chart, and that's our percentage of water vapor in the air. It's a very similar process to finding dew point as it is relative humidity. We're going to continue our example where we have a dry bulb of 20 degrees Celsius, a wet bulb of 10 degrees Celsius, so the air temperature is 20 degrees, the wet bulb, or the amount of water vapor in the air, is being measured at 10 degrees Celsius from our wet bulb. So our difference here, once again, is 10 degrees Celsius. Same process as before. Take your 20-degree row and your 10-degree difference column, and where they match up is your relative humidity. So that means that out of the air we have right now at 20 degrees Celsius in this wet bulb reading, our water level in that air is 23% full. So it's pretty dry. That means we got 77% still that could be filled with water. This would be a very dry reading. Okay, the next page I want to talk about is page 13 of the ESRT, and in particular, our station model map symbols. So where to always begin on the station model, I think is appropriate to start in the center. At the center of our station model, we have our amount of cloud cover. In this example, 3/4 or 75% of the circle is colored in. That translates to 75% of our sky is covered in clouds. So, very top left, we have our temperature, our air temperature. Notice that it's always measured in Fahrenheit. In this example, we are at a 28-degree Fahrenheit temperature. Bottom left, we have another degree reading, our dew point temperature. In this example is 27 degrees Fahrenheit. So our air temperature is very close to our dew point, and when our air temperature does reach our dew point, once again, that's when condensation occurs. That's when we would get cloud formation. Next, we have this little star. This little star on the left side of your circle represents snow. And down below, I have all the different present weather symbols. Any one of them could take the place of that star right there representing our snow. So if it is raining, you would just have a little dot. If it was snow showers, you could do the star with the triangle to show more intense snowfall. So the bottom right corresponds with precipitation or present weather as well. The 0.25 stands for that over the last 6 hours, we have accumulated, or there has been 1/4 inch of snowfall, 0.25 inches of snow. Next, right next to our snowflake, we have visibility. So visibility is measured in a whole number or a fraction. Here it is a 1/2. That means that our visibility, or how far we can see right now due to the weather conditions, is 1/2 of a mile. Top right might be the toughest part about a station model. It is our barometric pressure, otherwise known as our air pressure. It will always be written in 3 numbers on the station model. But what I'd like you to notice is in the parentheses, we have 1019.6 millibars. So we're measured in millibars here. The 3 numbers in our station model are not the actual air temperature. What you're going to need to do with those 3 numbers is follow one of 2 rules. So in this case, we are going to follow the rule on the left here, the less than 500, because our 196 reading, less than 500, you're going to want to add a 10 in front and a decimal before the last number. That process will get you your actual air temperature at 1019.6 millibars. Now, if you had a number in the top right that was 500 or more, similar process. However, this time you're just going to add a 9 in front, and you're going to continue to add a decimal before the last number. So when it comes to barometric pressure, you are either going to follow one of these 2 rules in order to gain the actual barometric pressure reading and not just the 3 numbers on the station model. In addition to the barometric pressure, we have our barometric trend, which is the air pressure increasing or decreasing? The little plus sign stands for that there is an increase in pressure over the last 3 hours. If there's a decrease in pressure, it would be a negative sign. Our 19 right here stands for a 1.9 millibar rise in the past 3 hours. So you're going to have to add a decimal place to get the true number that this 19 is trying to represent. And this slash stands for a steady rise. So it is increasing at a steady or consistent pace. Last but not least on the station model is our wind speed. Our wind speed is going to be measured with this line and these feathers on the end. So with this one symbol here, we are doing wind speed and direction. Now, on our line here, our feathers, we have this key right here. For a whole feather, it is 10 knots. For half a feather, it is 5 knots. So all you're going to do is add up the feathers you have. We have one whole, one half. This is a wind speed of 15 knots. And for folks who are not familiar with knots, we do have our conversion right here where 1 knot equals 1.15 miles per hour. So in addition to our speed, this also gives us our direction. So wind direction, always measured where the wind is coming from. In this case, the wind is coming from the southwest. I have my compass over here for you. There's not a compass on the diagram, so you're going to have to remember that north in the situation is up, and then we got east, south, and west, and everything in between. Okay, so last one I'm going to talk about here is page 14, and this is our layers of the atmosphere. So on our left-hand side of our scale, we have kilometers in altitude, how high we are off the surface of the Earth, all the way up from 0 to 160 kilometers. Each little line is increasing by 10. And on the right-hand side, we have miles. So miles, each line is only increasing by 5. So knowing what unit you're working with is going to be extremely important here. There are 4 sections, 4 layers of the atmosphere, and they all end in this ending sphere. We have our troposphere, which is where we live. We have the stratosphere just above that, mesosphere and thermosphere all continuing on into space. So these are labeled right on the chart, and we are going to have 3 boundaries between them. Each boundary ends in the phrase pause. So between our troposphere and the stratosphere, we have our tropopause, where the troposphere ends and the stratosphere begins. And if you'll notice, our tropopause, we can get the exact altitude of it by moving all the way to the left. It is just about 12, 13 kilometers up and about 5 to 7 miles up in the sky. In addition to marking all of our spheres and pauses, this chart is going to measure 3 variables. We're going to have temperature, pressure, and water vapor concentration. So temperature, our first one here. Our scale is just above the name. On the left-hand side, we have our low temperatures, and on the right-hand side, we have our high temperatures. As you can see, that as the line increases in altitude, temperature does not increase or decrease at a constant rate. The troposphere sees temperature decrease as you increase in altitude, and then it reverses in the stratosphere. So you could be asked, is the temperature of the air increasing or decreasing in the mesosphere? You would find the mesosphere and then notice the line for temperature moves to the left. That is a decrease in temperature as the altitude would increase. Next, we have atmospheric pressure. This is measured in ATM or atmospheres. So we have our scale measured from 0 to 1 atmosphere being at sea level on the Earth. As pressure decreases, our altitude is going to increase. So as you get all the way up in the thermosphere, we get closer and closer to zero pressure. Eventually, once we get into space, we lose all of that pressure coming from our atmosphere. So we start at 1, and as our altitude increases all the way up through the thermosphere, we decrease in pressure. And lastly, we have our water vapor concentration in the layers of the atmosphere. Notice that the water vapor concentration graph does not extend past the stratosphere. That's where we will lose all of our water. So it's only concentrated in the troposphere and a little bit in the stratosphere. So nearly all our water is in that troposphere. So I hope this was helpful for you. Please let me know any questions you have, and have a good night.